So join on in there, and we'll discuss this example as well as the rest of the lecture content today. So this is a question about resonance. They're giving us compound A and compound B. And we're going to identify which of these two compounds has a greater resonance stabilization. So you get more stabilization if you have a greater number of contributors. Especially if there's formal charge that needs to be spread out over more atoms. The more of those 5 patterns we talked about I can use to shift the electrons around and move the formal charges to different atoms. Got to follow those 5 patterns, but if you're using those specifically and you can move the charge to a variety of different atoms, that one formal charge would be spread out over maybe 4 or 5 atoms. That would be really stabilizing because each atom would only carry a very small quantity of partial charge. I wouldn't have any one area of large formal charge making my structure unstable. In this case, though, my starting compounds are both neutral. They don't have any charge. So I'm not worried about stabilizing them through formal charge. I just want to see which one I can draw more contributors for. Which one has a greater variety in the ways the electrons can be positioned. That one should allow more resonance for the electrons or for the resonance to be spread out over more atoms. So you're probably noticing for the 6-membered ring part of this, that creates one of the 5 patterns for resonance. So whether I show the electrons positioned there or whether I show them positioned here, those two structures are in resonance because if I start with the electron pair here, I can shift it up here and move this here and move that there. And so in reality, none of these pi electrons are localized between just 2 individual carbons. They're all spread out over all 6 carbons, which stabilizes those electrons in molecular orbitals, attracting the multiple nuclei at once. So we have that in both these structures. So we can't use that to differentiate between them and decide which one is more stable than the other. What we need to look for are some of the other patterns. So both of these structures also have the pattern where I have a pair of pi electrons shared between elements of different electronegativity. The oxygen can pull these electrons up over here just like it can over there. So in that area of the structure, so we'll just look at compound A first. I want to redraw everything else as it's initially shown. Helpful to draw in the lone pairs where they have them. So here if these electrons swing up, it creates an alternative resonance contributor. It's a minor resonance contributor because the formal charges here make it significantly less stable than the original structure that was neutral and had no charge. But it's still significant. That's one of the 5 patterns we talked about. And in creating the positive here, I start to see something I wouldn't maybe have otherwise seen if I just look at the original structure, because here this carbon has 4 bonds already. And here it only has 3 bonds, so it can accept more electrons. So what I've created here now is a carbocation allylic to this double bond. And so that creates another pattern. So once you follow one of the patterns, look for other patterns that exposes or other opportunities for electron movement that opens up for you. So if this pi electron pair moves up here into this bond, didn't leave much space for that to be shown, but I want the arrow to be pointing at the space between these 2 carbons. If that moves up there, it creates another contributor. So my oxygen would still have the 3 lone pairs making it negative. Now I've got a double bond here. I've got the other pi electrons still positioned in the same spot. Everything else is the same. I haven't moved any of this stuff around. But now I have a positive here because this carbon initially had 4 bonds. I moved the pi electrons away. Now it only has 3. the hydrogen is obviously still there. So now I've got another allylic carbocation. Now this carbocation is allylic to this pi electron pair. So these two can move over and create another contributor, right? So I'm looking for as many contributors as possible. That helps me to recognize more contributors there are, the more stable the structure will be. Or in other words, the more pairs of pi electrons that can get involved in the resonance, the more atoms the molecular orbital can extend over that hold those electrons to stabilize them and allow them to attract to more nuclei. So if this pair of electrons moves in there, now my membered ring has electrons, pi electrons positioned here, here. This double bond is still over here to the carbon. A little sloppy there. This is still here, and still got that oxygen there with its two lone pairs. And now my positive charge is located on this carbon, because this carbon had 4 bonds. When the pi electrons move away, now it only has 3 bonds. And now I have another allylic carbocation. So this pair can move back down here and create another structure. That looks like this. And now my positive charge is located here. So at that point, I'm seeing, okay, this positive charge is not allylic to this, so I could move these electrons in here, but then that just goes back to the original structure. So that's pretty much as many resonance contributors as I can draw for that structure. And what I'm noticing is this positive charge that's created in these minor contributors is spread out over 1, 2, 3, 4 atoms. And that helps to stabilize that somewhat. So that looks pretty stable. So the resonance in compound A is pretty significant. I can also imagine this lone pair of electrons on the oxygen moving in here, but that would make a 5-bonded carbon unless I also move this pair of pi electrons out to the carbon. But that would put a lone pair on a carbon, which is a really unstable negative. So that resonance probably is not very significant and probably not worth really considering, because if this pair of electrons moves in here, that would make a positive on the oxygen and a negative on a carbon, and being such a small atom, carbon with a negative is really unstable. So that's probably, although it does follow one of the 5 patterns, probably not a very significant contributor to the resonance. So this is, for the most part, my significant contributors, and the stability is going to depend on how many of those I can draw. For molecule B, and it also turns out for molecule C, I can actually involve the lone pairs on this oxygen in a way that's not going to work so well with compound A, and that's where the difference lies to help you answer the question. So if we look at compound B, we'll see something that wasn't really possible in compound A, and that is the oxygen's lone pairs, or one of the oxygen's lone pairs, can get engaged in the resonance that involved this positive on the ring. So we're still going to do things in the same way, right? We could still just move the electrons in the ring around. That would be one way of looking at resonance here. Alternatively, we can move these electrons up, as we showed initially over here. That would create a positive at this location, and that would attract the electrons out of the ring, so we can still do the same thing again. And if these electrons moved out, that created a positive down here, which is what we got over here. And so the next pair of electrons moved over, so we can move these over here. So I would have all the same contributors that we saw for compound A are also possible for compound B. But once I get to this specific one, where the positive is on this carbon here, the same positive it was on in this molecule over here, now it's set up for one extra contributor that compound A was not capable of forming. Oh man, I got a cat fight going on over here. Alright, I'm going to try to ignore that. Oh no. What a shame. Oh, this isn't a hydrogen. This is just a methyl group. Alright, so as we were saying, these electron pairs shift around. I get the positive at this location. So when the positive was on that location before, the oxygen was 1 carbon away. Its lone pairs couldn't get in there. None of the 5 patterns would allow those lone pairs to come in here and stabilize that positive. But now the positive forms right on the carbon that the oxygen is directly attached to. So this lone pair can now move in here and create an extra contributor that has complete noble gas configurations for all the atoms. So it's even more significant than these other ones with the positive charges. And that really helps to add to the stability of the resonance that structure is creating. So just to show that other contributor. So once this oxygen moves its lone pair in there, I form a double bond here. And now my positive resides on the oxygen. So this contributor here is a little bit more stable than any of these other ones that have formal charges. Obviously the one with no charges is the most stable and by far the major contributor. But each one of these minor contributors adds a little bit to the stability because it adds to the delocalization of the pi electrons over more atoms. And when that OCH3 group is attached to the ring, here or here, that's a possible extra contributor where the positive charge also resides on the oxygen, and the lone pairs of the oxygens can move in and get involved in that resonance existing in an orbital that extends over the whole system. In the case of compound A, it's not really possible, as we showed, because the positive never really resides directly on the carbon that the oxygen is attached to. There's no way for it to move its electrons in without creating an especially unstable situation. So for part A, the answer is compound B is going to be a little bit more stable than A, or at least the resonance is going to stabilize it a little bit more than the resonance in A, because there's an extra contributor I can draw in B that I can't really draw in A. And the same thing for compound C. C is going to be more like B, and the reason for that is the same reason. As I shift the electrons around, there's one contributor that where the positive charge is created on this carbon, so that allows the lone pair from the oxygen to get involved in resonance, creating an additional resonance contributor and additional stability. All right, so I hope that helps to explain and answer that question. If anyone has any questions about that, please speak up. All right, so we'll continue then with our discussion from Chapter 3, where we left off on Thursday. Thursday we talked about Pka values. So you want to recall that Pka usually ranges from about -10 up to about 50. It's a more relatable scale than the Ka scale. Recall that the Ka scale ranged from 10 to the -50th down to 10 to the 10th. Right? So very large numbers and very small numbers for my Ka values. And so by taking the negative log of those, we make the scale a more relatable scale. That's the main reason we use Pka. But we know that a very tiny Ka value or a larger Pka value, both of those exist for weaker acids. Right? So if you can remember back to Gen Chem 2, the equilibrium constant, the Ka value, tells me how much the acid reacts to produce products versus how much it remains in its original form as a reactant. So if that ratio is very, very low number, it's because I have a lot more reactants than products, and if it's a weak acid, that's what I expect. Very little of the reactants will actually form products. Most will stay in the form of the reactants. So we know that we can judge how acidic a molecule is, or how much that molecule will react with water, by donating a proton to the water by looking at the ratio, the Ka ratio, or the negative log of that, which is the Pka. And we know the lower the pKa value, the stronger the acid. And anything that's negative is going to be strong enough that if I put it in water, virtually every single molecule will react by donating an H plus to a water molecule, right? Because that's what acids do. They donate protons or H plus ions. So that was the quantitative analysis. We were using numbers to actually quantify how much more acidic one thing was than another. And we said if I had a pKa unit of, say, 9 versus a pKa of 10, one pKa unit difference is actually a factor of 10 in terms of how acidic the substance is. So the lower pKa value is more acidic, and that means that if a molecule is a pKa of 9, it's about 10 times more acidic than a pKa of 10 because of the way that log function works when we take the log of the Ka values in order to calculate the pKa values. So today, though, we're going to focus on how to judge the strength of an acid qualitatively by looking at the structure of the molecule. So we want to be able to recognize which features on a molecule affect its stability when it has a charge, and that's going to affect how likely it is to take on a charge or alleviate a charge in an acid-base reaction, right? So recall, acid-base reactions, there's always a change in the charge for the structure when it reacts as an acid or a base. If I have a neutral compound and it acts as an acid, it donates the H plus and it's left over with a negatively charged conjugate base. If I had a positively charged molecule that was acting as an acid, when it donates an H plus, it produces a neutral conjugate base. So either the original acid or its conjugate will always be charged. And that's what we're going to be focusing on in this analysis. We're not really going to be looking at the neutral version of the structure because a neutral molecule always pretty much looks stable unless it has a broken noble gas configuration, which isn't usually going to be the case. It's hard to judge whether one's more stable than the other, right? If I'm just looking at HCl versus this butane molecule, and I don't know, neither of them look unstable because they both have complete noble gas configurations and zero formal charge. How do I know which is a stronger acid? Well, I know HCl is because from experience, but I can't really explain that unless I look at the charges on their conjugates. So if a structure is already neutral and we're trying to judge whether it's going to act as an acid, we want to look at how stable is it going to be after it donates the proton. Because if we can look at the charge and talk and invoke the rules we're going to talk about today that help us explain when the charge is stable or not, if it's stable, we can say, well, that's a stronger acid because it always donate the proton to produce a stable product. If upon donating the proton and the electrons stay behind, I get a very unstable charge, then that original compound would have been a very weak acid because very few of those molecules would ever donate a proton if it produces something that's so unstable after doing so. So we're going to look at a variety of factors today and try to rank how important those factors are in judging the strengths of acids and bases. So which is a stronger acid here? Well, clearly we know HCl is a much stronger acid. If we wanted to, we could look at its pKa value. That will really help us verify our predictions if the pKa values are known. And so the pKa value for this is about -7. And the pKa value for this is about 50. So that's the difference is 57 pKa units. Or in other words, HCl is 10 to the 57th times stronger than this butane molecule. And the difference there has to do with the stability of the charges that result. Right? So if we can use the pKa values to say that HCl is much stronger as an acid, that means that its conjugate or its charged resulting conjugate base must be much more stable than the other one. And that has to do with chlorine's ability to stabilize a charge versus carbon. So let's just talk about that real quick. Why is chlorine able to stabilize a charge better than carbon?
Is it because chlorine has more protons, so like the negative to positive ratio is not as bad?
Very good. So the charge on is most affected by the size of the atom. Or in other words, the positive to negative charge ratio. So if we look at chlorine, chlorine has 17 protons. If we give it a negative charge, it has 18 electrons. So if I divide those two to create a ratio, and I divide 18 divided by 17, I get a value of 1.06. So there's only about 6% more negative than positive in that ratio. Versus carbon, which only has 6 protons, if I give it an extra negative and I give it 7 electrons and divide to find its positive to negative ratio, 7 divided by 6, that's 1.17. So that's about 17% more negative than positive. So that difference might not seem like a lot, but it's a lot. It's a very significant amount. And so the more protons I have, the less unstable, the less extra instability there will be if I put just one extra electron in there. So that's one factor. Another factor is electronegativity. And we'll see more examples of this in the upcoming slides. Chlorine is more electronegative than carbon, and so it naturally attracts electrons better. So putting one extra electron around it, since it's an atom that naturally pulls electrons in, it'll get pulled in nice and tightly to its nucleus for the most part and stabilize there, versus the electronegativity of carbon being only 2.5 versus 3.0. It just doesn't hold its electrons that tightly. It doesn't pull them in as close to its nucleus. And so the electrons are repelling one another more than they are being attracted to the nucleus if the nucleus doesn't really attract them that much. And that also affects the stability of the negative charge. So there are really two factors there that you can look for. This is the bigger factor. So as long as two elements have different numbers of layers of electron clouds and significantly different sizes like this, that will usually be the deciding factor. So let's look at some of the other factors. So we just talked about that. The atom that actually carries the charge. Even before that, we talked about the quantity of charge a little bit. We said if the molecule initially is neutral, what's going to create a negative? That's going to be unstable. Well, what if the molecule already had a charge to begin with? If it was already positive, is that going to make it stronger than if it were neutral to begin with? Yes, because if it's already positive, it's even more likely to donate an H plus to produce something that's neutral. So there are definitely going to be exceptions to some of these ideas, but if we put the ideas together, usually they can be used cumulatively to come up with a good answer. So the textbook doesn't really focus on this enough, but generally, if there's already a positive charge, it's going to make the acid more unstable. Obviously, the formal charge makes it unstable, so giving away an H plus and alleviating that charge is going to be more likely to happen. The acid is going to be reacting more often or stronger than one that's already neutral that has to stabilize somehow a negative once it gives up the proton. It's going to be much more likely to grab that proton back and go back in the reverse direction than something that's produced that has no charge at all. So I would add to this another factor and just say the quantity of charge on the original acid. And if it's an acid, we can say a more positive charge, stronger acid. So that is when you're comparing something that's already positive versus something that's neutral. Or something that's negative versus something that's neutral. If it's already negative, it's not going to want to give up an H plus and form a second negative. That would be even more unstable formal charge unnecessary. So that's a really big factor. The other factors are when you're comparing equal quantities of charge. Right? So if I'm comparing a chlorine with a negative versus a carbon with a negative, well, the first thing I want to look at is what's the atom that actually carries that negative? Well, there's a difference, obviously, between chlorine carrying a negative versus carbon carrying a negative. And so we really don't have to go further and look at these other factors if it's the same element carrying the same amount of charge. But these other factors will be relevant. I'm sorry, I think I misspoke. We don't need to look at these other factors if it's a different element carrying the same amount of charge, or if they're carrying different quantities of charge. The first two factors would cover that. But we look at resonance, induction, and orbital if it's the same element carrying the same quantity of charge, and that often does happen. So we want to be able to look at those nuances and invoke these different factors, which we'll talk about one by one as we go through. So the textbook takes the atom, resonance, induction, orbital, and converts that into an acronym. Since we're using the quantity of charge, I'm going to put a C in front of that acronym. And then later today we're going to talk about solvation, and so we're going to put an S for solvation at the beginning of that as well. So the full acronym that really includes all the relevant factors isn't really aereo as much as it is scareo. So we'll talk about that as we go through. All right, so we talked about the atom. Here's another great example, carbon versus oxygen. So if butane acts as an acid, it keeps the electrons behind and produces a negative charge on a carbon. If this alcohol reacts as an acid, the oxygen pulls the electrons behind and donates the proton to some base, what's going to be produced is a negative on the oxygen. So what's the difference? Well, carbon has 6 protons. Now it has an extra electron. Oxygen has 8 protons, and now it has an extra electron. So the charge ratio here is a little bit closer to 1. It's not quite as unbalanced as it is here. And so there is a slight difference in size, not a big difference. But there's also a difference in electronegativity. Right, the oxygen being significantly more electronegative than carbon. That means that it just also naturally, and this is also due to the extra protons it has, it naturally pulls the electrons in closer, and so they're not, the repulsion created by having too many negatives in one area is offset somewhat by the fact that I've got extra positives to pull those in tighter and form stronger attractions with the nucleus. So if we looked at the different pKa values for an alcohol, like propanol, versus an alkane like butane, we see that propanol's pKa value is around 16 and butane's is around 50. It's a big difference. So that's why the atom comes before resonance, induction, or orbital in the acronym, because if it's a different atom carrying the charge, that often makes a very big difference in the pKa values that those acids will have with respect to one another. So after I look at the atom, if I'm comparing two molecules that have the same atom carrying the charge, and they have the same quantity of charge, the charge quantity is the same. So if they have the same quantity of charge, meaning they had the same charge to begin with, the same atom is carrying the charge. So in this case, there is no charge. So if I'm looking at how acidic this is, or how likely it is to donate this proton versus how likely this one is to donate its proton, I want to look at how much charge is going to be created and where that charge is going to reside once the proton is lost. Because right now they both look perfectly stable. There's hard to tell the difference between them. So I know if this one acts as an acid, the electrons will be kept behind, and I'll produce a negative on that oxygen. If this one acts as an acid, the electrons will be kept behind, and it'll produce, again, a negative on the oxygen. So if I'm trying to compare which is a stronger acid, I can say whichever one's a stronger acid will be more likely to donate the proton, and that'll produce a charge that's more stable. If the charge is unstable, then it will be more likely to just pick the proton back up and go back to its original form, meaning that the original form wasn't that strong or reactive and that it was weaker. So the difference here, though, is resonance, because this oxygen, its extra lone pair and negative charge associated with that is concentrated or localized only on that oxygen. That's a lot of repulsion. The neighboring atom is sp3 hybridized. The neighboring atom does not have a p orbital to overlap with any p orbital that would be on the oxygen and create resonance. So there is no resonance. So that means these lone pairs exist in sp3 orbitals, but the main point here is that they're localized only on the oxygen. They can't be spread out through resonance. On the other hand, this structure over here, there is a pi bond between the carbon and the oxygen. And so that means those pi electrons exist in p orbitals above and below the plane of the atoms. And so if one of the lone pairs on the oxygen hybridizes into also a p orbital, the overlap there will allow for resonance to occur. And I can also recognize that this lone pair is allylic to this double bond. So I can move it in and push these electrons up here and create an alternative resonance contributor that spreads out the negative charge to the other oxygen. And so this, as an acid, produces an unstable conjugate. So it's a relatively weak acid. It doesn't produce a very stable negative charge. That negative is concentrated on one atom. That oxygen always carries a formal negative. How much of a negative does the oxygen carry on the other molecule? Well, in this contributor it carries a -1, and the other contributor it carries 0. You got to remember that in resonance, neither of these exists. What exists is the average of those two, or the hybrid. And so if each oxygen has two lone pairs that are not delocalized, but each oxygen has a negative in one and 0 charge in the other, then that's average is only a -1/2 on each. So neither oxygen really has the instability associated with a full formal charge when they each carry only half of a negative charge. So it's way more stable. And that's reflected in the pKa values. The pKa value for ethanol is 16. The pKa value for acetic acid is about 5. So 11 pKa units difference means that acetic acid is 10 to the 11th or 100 billion times stronger as an acid versus ethanol. And that's due to the extra resonance that occurs there. So you always want to be able to look for that. If you see a negative charge or a positive charge, look for a resonance to stabilize it after you analyze, if you're comparing multiple molecules, after you analyze how much charge they're carrying, what atoms carrying the charge. If you have a situation where resonance can help to stabilize that charge, that's the next most important factor there. Any questions about that?
What does the C stand for again?
Charge. It really means the quantity of charge. So in this case, since the molecules had the same charge and their conjugates had the same quantity of charge, that really doesn't help us to distinguish between them. And since in both cases it's the same element or atom carrying the charge, that doesn't help us distinguish between them. And so that's why we have to go to the next letter in the acronym to find the difference.
I have a question about
Sure.
the resonance grid. It's not. Is it not always like they would be sharing an equal half negative charge? Aren't there cases where it could be a different? I don't know how
Sure.
a different kind of it's not always half and half.
Correct. In this case, it's half and half because of the symmetry here and the fact that, if I made a dotted line right down the middle, this part of the molecule is exactly as the other, so there'd be no reason why one would carry more negative than the other. If I had a situation like this, and I were looking for resonance to stabilize this negative charge, I can see that occurring. The pi electrons would have to move on to a carbon, though. So if I were to look at the other resonance contributor created from that, where it had a negative on a carbon, well, as we were saying in the last slide, carbon can't stabilize a negative nearly as well as oxygen can. So in that case, if I were looking at the hybrid, I really don't have much space, I'll just draw it here, I guess. In that case, if I were looking at the hybrid, since this contributor is significantly more stable with the negative on the oxygen than the other contributor with the negative on the carbon, there's going to be a much greater quantity of partial negative on the oxygen and only a very small quantity of partial negative on the carbon in comparison. So it depends on if you have a resonance hybrid or average you're drawing from. different resonance contributors, if they're equally stable, then they equally affect the average. If one of the contributors is more stable than the other, that contributor affects the average more, and the charges on the hybrid or average would be more similar to the major contributor than to the minor contributor. All right, so if I can't distinguish between two structures based on the quantity of charge, the atom carrying the charge, or resonance, then I look for induction. So in this example, we can see the presence of induction, right? So here, if this is an acid, it gives away the proton, keeps the electrons behind, and so I create a conjugate base that is the same as the one we just looked at on the last slide, with the negative stabilized through resonance with shared half and half over both oxygens. If this molecule does the same and the electrons stay behind, I create a similar situation where I'm creating a negative on an oxygen. So same quantity of charge on both of these, same atom carrying the charge, and they both have the same type of resonance to stabilize the charge actually over both oxygens instead of just one. The only difference is the presence of these chlorine atoms. So this will help us illustrate how induction works. So as we've said a little bit so far this semester, induction results from electronegativity differences and causes electrons to shift around more toward the more electronegative atoms. So we talked about that in Gen Chem, but we didn't really call it induction. So these chlorine atoms create induction, right? Chlorine's more electronegative than carbon. And having three of them here means each one of those is attracting the electrons that it's sharing with the carbon. So the cloud of electrons here is just pulled more toward the chlorine than toward the carbon. And what does that do to the carbon? Well, if all the electrons it's sharing are pulled away from it, it makes it quite partial. It gives it quite a large partial positive. Each chlorine pulls some electrons away. It's not going to have that much around it, so it's not going to have enough negative to balance out its charge there. And so what that means is that that positive is now pulling electrons away from this carbon. Right? So we normally think of two carbons as having the same electronegativity, but if one has a large partial positive and the other doesn't so much, that's going to cause it to attract electrons more. So the charge on an atom affects its electronegativity. The more positive the atom is, the greater its electronegativity is compared to what it would be if it didn't have that charge. So now that this induction causes this carbon to become positive, it starts to pull these electrons away. And that creates even more of a positive here. And that positive helps to attract electrons a little bit away from this oxygen. Right? So the problem with this structure is that there's too much negative around this oxygen and also around the other one due to the resonance. But when I have too much negative on my oxygen atoms, it's unstable. So if I can pull, I can't really do anything about the lone pairs. Those are stabilized through resonance. But induction doesn't really stabilize things in the same way as the resonance. It's not actually delocalizing the electrons or the lone pair electrons and moving them in. But it is pulling away shared electrons, right? So induction is always the attraction of shared electrons toward a more electronegative atom, or the effect of a more electronegative atom on the shared electron. And so as this chlorine pulls electrons away from the carbon pulls electrons from the neighboring carbon, that carbon pulls electrons away from the oxygen, the shared electrons get pulled away a little bit from the oxygen. So even though it has all these lone pairs all to itself, it doesn't really have as much of the shared electron density around it. That gets pulled away. So it's not really as negative as it would otherwise be. So that also alleviates some of the negative charge, or in other words, spreads it out over these carbons and a little bit onto the chlorines. So that might not seem like much of a factor to you, and it's really not that much of a factor, which is why it's one of the last factors we consider in the acronym. But it does create a significant difference in pKa values. So without those chlorines attached, the pKa is about 5. If I put all three chlorines on, the pKa is about 4 units less than that. So if I'm just comparing those those two, I mean, every chlorine I add, I see changes the pKa a little bit. Having 2 chlorines makes it lower than 1 chlorine, etc. But comparing no extra induction versus the induction of 3 chlorines, each one pulling electrons away, creating a larger partial positive to pull electrons away, to help pull electrons away from the atom that would become unstable and negative if it lost the hydrogen. This molecule is more willing to give away that hydrogen and create the negative. It's a stronger acid because that negative can also be stabilized through induction and not just resonance. And the difference is not big. It's only a 4 pKa unit, but that means it's really 10 to the 4th times stronger, or 10,000 times stronger. So it's still creating a pretty significant difference between the acidity of those two structures. There's also induction in this comparison. So we said the difference here was about 11 pKa units. So we can say acetic acid is about 10 to the 11th, or 100 billion times stronger as an acid. Part of that is the resonance. The main part of that is resonance. But that difference also is influenced by the induction of this CO double bond, right? So we said once this loses a proton and creates the negative charge on the oxygen, that's stabilized through resonance with the other oxygen. But this CO double bond also affects it through induction, because these electrons aren't just shifting up through resonance, they're also attracted to the oxygen through the electronegativity difference there, which is what induction is. So when I have the oxygen being more electronegative than the carbon, and it pulls these electrons up, that also helps to create a large partial positive on that carbon, which attracts the shared electrons and alleviates some of the extra negative that's just around that oxygen, making that oxygen unstable. So the difference here is both a combination of the resonance that stabilizes the negative of both oxygens, as well as the extra induction of the CO double bond creating some positive here to pull some of that electron density off the oxygen so it's not so unstable, meaning that the original acid would be more likely to give out the proton, making it a stronger acid if it creates a relatively stable conjugate. So then the other letter in the acronym, so this is the least significant one. The O stands for orbital, and that has to do with what type of orbital the lone pair exists in. So we saw the difference between sp3, sp2, and sp orbitals. We know that an sp orbital is a 50-50 mixture of s and p, so it's relatively compact, more shaped like an s orbital than the other ones that have a higher proportion of p character mixed in with only one s. So this one here is only about 33% s, and here I've only got 25% s. So it's more elongated. Its shape looks more similar to an actual p orbital because there's more p mixed into that shape. So the effect that that has is that if there's a lone pair in one of these orbitals, the lone pair is going to be more stable in the more compact orbital where it can get closer to the nucleus, right? So in the shape of these orbitals, this is where the nucleus is. There's a node here, the nucleus is here. So if my orbital is elongated, most of the electron density is out here, not very close to the nucleus. And so this comes into play when we're looking at the difference between sp3 hybridized atoms that a hydrogen might be sharing electrons with versus sp2 versus sp. In the sp3 situation, if this were to act as an acid and lose that proton and the electrons were to stay behind, those electrons would be in an elongated sp3 orbital. They wouldn't be that close to the nucleus. They wouldn't be as stabilized by the attraction to that carbon nucleus. If this molecule did the same thing, its electrons would be in a more compact sp2 orbital, so they'd be closer to the nucleus on average, more stabilized. So these molecules are more likely to do that. Not a big difference, but a significant difference 10 to the 6th. Ethylene is 10 to the 6th times stronger as an acid than ethane. Or a million times stronger. It's still very significant. In this case, the compact sp orbital that would exist here, much more compact, it puts the electrons pretty close to the nucleus. So this is actually getting close to being acidic enough to actually react with water. Still very weak acid. Still a very large value for the pKa. On the scale it goes from negative 10 to 50. It's on the higher end of the scale. There's a big difference here though, and that's the difference that orbital shape makes. So even though it's the last letter in the acronym, and it's usually our last thing that we look at to differentiate between structures, it can really make a big difference, especially when it's sp, because that one is so much more similar to an s orbital and more compact. It really does stabilize the electrons and hold them pretty close to the nucleus. So this molecule is much more willing to give up a proton if the electrons that stay behind can be stabilized and held closely to the nucleus that they're surrounding as a lone pair. Alright, so let's take a look at this molecule here. See it? Look at this one as an example. If I had a strong enough base, some base that had a pair of electrons, maybe it was really negatively charged, maybe it had a -2 or something really stable about it, that would make it a strong base. So if I had the strongest base you could imagine, just generically for the sake of argument, which of the hydrogens on the structure would be most likely to be removed? Okay, so we're analyzing all the different hydrogens that are attached here. They're not obviously shown. There's no hydrogen here. This carbon already has 4 bonds. There's one here. I mean, there's a couple here. There's a couple here. There's one here. Here. Just draw them all in real quick. We've got a lot of options. There's no hydrogen here or here. Those are sp3 hybridized atoms, but there are hydrogens here. So first off, why would a very strong base be required? Well, none of these hydrogens have low pKa values. They're all pretty weak. If I remove any one of these, I'm going to create a carbon with a negative charge, and that's really very unstable. So I'm looking at pKa values above 20 most likely for atoms. That's really unstable to put a negative on a carbon like that. But I still have to judge if one of these hydrogens were removed and I left a negative behind on that carbon, which would be the most stable site for that negative. Right, so if we use the acronym, all these hydrogens are bonded to carbon, so the atom carrying the negative charge that would result when the hydrogen's lost would be a carbon in each case, so that can't really help us to distinguish between them. So then we want to do these in order, so don't jump ahead. Is there a resonance possibility if one of these protons is removed? And the answer is yes. This proton here, or this one, they're equivalent, or actually any one of these three, or actually any one of these three. If any one of those were removed, there would be some resonance stabilization for the negative that results. So let's take a look at that. So if my base picks off one of these protons and the electrons behind, what would that do for my structure? That would create a negative here on a carbon. As we said, that's really unstable. So we know this hydrogen's pKa value is pretty high, but compared to the other hydrogens in the structure, it's one of the lower ones, because when this exists, normally I'd think of it in an sp3 orbital, but in this case, it would actually exist in a p orbital because the p orbitals existing in these two carbons to create the pi bond could overlap side by side with it. And so that means instead of this carbon carrying a negative, it would actually be stabilized through resonance and pushed onto the other carbon. And so in the hybrid, in the hybrid structure, the negative would exist on this atom And when the electrons moved in and pushed this lone pair over here, it would also exist on this atom. So my resonance would look like this, and I would have only half of a negative on one carbon and half of a negative on the other, and that's going to be a lot more stable than a full negative on any one of these carbons. So you could make the same argument with one of these hydrogens or one of these hydrogens. So, I mean, either way, you're getting to the same point. The resonance helps you answer that question first. There's no highly electronegative atoms, so there's no real induction that would help to stabilize that negative. The orbital, if I looked at that first, that factor would actually make me think that this hydrogen is the most acidic. Because if my base picks off this hydrogen and the electrons stay behind, I would get, I would get a structure that looks like this, with my negative on an sp2 hybridized carbon with an sp2 orbital holding it relatively close to the nucleus. So it's hard to say for sure whether the resonance stabilizes the negative more by spreading out over two atoms, or whether the more compact orbital would stabilize it more. But that's why we have the acronym in the order we have it in. So use it in order. There's only really one exception I expect you to know, which we will talk about today. Otherwise, if you use the acronym in order, you should come up with the best answer most of the time. And that'll be the answer I'm looking for on exams. So there's only one exception I might give you. So let's take a look at an example here. So we have ethanol versus propylene. Here I'm imagining which is a stronger acid. If the ethanol gives up a proton, the electrons stay behind. Again, if the molecules start off neutral, I can't really analyze which is more stable. They're both quite stable. So if they're going to act as acids, I'm looking at the possibility of them giving up a proton, keeping the electrons behind, to see how stable are those electrons and how stable is the charge that's produced. Because if I'm looking at a formal charge, I can use these factors to differentiate between which charge is more stable. So if this gives up a proton, if this gives up a proton, and the electrons stay behind, I'd produce a negative on a carbon. So which is more stable? Well, using the acronym in order, I would look first at the atom carrying the negative charge. And so just also mention, we did add a C in front of that for the quantity of charge, and since they both carry the same amount of charge, that factor is not going to be able to distinguish between them. That's why the textbook leaves that out, because most of the examples the textbook focuses on, the molecules you're comparing have the same charge, but on exams you might see some with different charges, so you got to look at that first. So if they both carry the same quantity of charge, the next factor to look at is the atom that's holding the charge. And as we said, oxygen is slightly larger and more electronegative, so it pulls the electrons in much tighter and stabilizes them much more effectively than carbon. And we can see that borne out in the Pka values. So the carbon does have the advantage of having resonance. The electrons can shift in here. This is an allylic lone pair, move to the other atom. That would create an alternative resonance contributor, and the resonance hybrid would have half the negative on each end of the two end carbons. So here we're seeing there's a big difference here. The oxygen is so much better at stabilizing a negative than carbon, even when there's resonance to spread that negative of the carbon on two different carbons. It's still not nearly as stable as having the negative on the highly electronegative, slightly larger oxygen atom. And that's a big difference there in how often those molecules might give up a proton. Again, the higher pKa means it's less reactive. The weaker acid is not going to give up that proton, because even when I spread out the negative charge to resonance on a carbon atom, it's just not good at stabilizing a negative compared to an oxygen. Yes?
I have a question.
Yeah.
For the propylene, if you move in the lone pair, so does that carbon not have a hydrogen attached to it? Like the double bond? Plus the single bond plus the hydrogen?
This carbon here?
Yeah.
No, it has hydrogen. So that's why I need both of these arrows. So I can't just, you're right, I can't just move these in and create 5 bonds. The other ones have to move out at the same time. So when I show that hydrogen, I'm still, I can't exceed 4 bonds. That's definitely true. So that's why in the allylic lone pair, I have one arrow to show the allylic lone pair moving in, and another arrow to show the allyl double bond shifting out, so that I avoid the 5 bonded carbon and I can create an alternative contributor. And then the hybrid would be the average of those two. Alright, so here is the only exception I actually expect you to know. You might want to memorize this one. And the reason for that is because it's actually common and relevant to some reactions that we're going to see later. So if you can remember this one, that would be really helpful for you. So if we look at the acronym in order, looking at the quantity of charge first, they're both neutral, so they'll have the same quantity of charge. Trying to decide which is a stronger acid. If this gives up a proton and the electrons stay behind, I'll create a negative on a carbon. If this one gives up a proton and the electrons stay behind, I create a negative on a nitrogen. So based on the acronym, I would normally expect this molecule to be a stronger acid, because when the electrons stay behind on the nitrogen, the negative charge is going to be more effectively stabilized. It's a more electronegative atom. It's slightly larger than the carbon. The carbon can't stabilize the negative very well compared to oxygen. The oxygen has the extra proton in its nucleus to pull the electrons in and stabilize them better. So that's why this is the exception. So even though the atom carrying the charge is different, and that normally is enough for me to distinguish which is a stronger acid, it turns out when I look at the actual pKa values here, I see that the acetylene's pKa value is about 25, and the ammonia's pKa value is 38. So 13 pKa units difference, which is 10 to the 13th. So the acetylene is 10 to the 13th times stronger. It's going to give up its proton a lot more readily than this nitrogen will. And so this particular example is an exception, because normally the type of orbital holding the electron pair doesn't matter that much. But in this case, when we're comparing sp versus sp3, there is enough of a difference in the shape of the orbital to offset and then some the fact that carbon normally can't stabilize a negative as well as nitrogen can. So typically nitrogen stabilizes a negative better than carbon. Here the only exception you need to know is if the carbon specifically has an sp orbital to stabilize that negative versus the sp3 on the nitrogen, because we see the steric number here is 4 versus the steric number of 2 over here. That sp3 orbital is so much more elongated than the sp that causes the normal situation here to be reversed, and the molecule that we would normally expect to be the weaker acid is actually the stronger. So if we have this equilibrium going, it should go toward the right hand side, right? We talked about this before. We said in an acid-base reaction, the equilibrium is always going to shift more toward the side with the higher pKa. The more stable or weaker substance is going to be the side that the equilibrium favors. So if you're given the pKa values, you know it's always going to favor that side. If you're not given the pKa values and you're given an equilibrium, you have to decide which side the equilibrium favors. You want to look at the charges and use the acronym to determine which charge is more stable. So again, this one won't work if you use the acronym, but we just talked about it, so you want to remember that the sp orbital stabilizes a negative charge on a carbon better than an sp3 orbital stabilizes stabilizes a charge on a nitrogen, even though nitrogen normally is better at stabilizing a negative than carbon if the orbitals were the same. Here's another example. So I might give you a structure and ask you to rank the hydrogens on that structure. So here we've got, we'll do this one on the left first. I want to look at each possible hydrogen if it were given away and use the acronym to compare the negative charges that are left behind and look at their stabilities. So if this hydrogen were gone and the electrons stayed behind here, I would have a negative on a carbon. If this hydrogen were given away and the electrons stay here, I would have negative on an oxygen. Same thing here, except here if the electrons stay behind, I've got another negative on a carbon. Versus here, again, on another pair of electrons on a carbon. So each one of these protons given away leaves behind a negative charge, so they each leave behind the same quantity of charge. That won't distinguish between them. If we look at the atom holding the charge, this is where you got to be a little bit careful. This oxygen's holding a negative. In each other instance, it's a carbon, but you have to kind of look for the resonance before you make up your mind, because in this case, what you'll see is if this lone pair on this carbon is allylic to this CO bond, it can shift in here and actually move the negative to the oxygen. So the atom carrying the negative isn't necessarily the atom where the negative first forms. If the negative is spread out over multiple atoms due to resonance, I have to look at all the atoms carrying the negative. So in the case of this negative charge up here, it's actually going to be mostly on this oxygen, because it stabilizes the negative better than the carbon, and only a little bit on the carbon. So in this case, I've got oxygen stabilizing a negative, plus the carbon helping out a little bit through resonance, versus oxygen stabilizing a negative without any resonance, versus carbon stabilizing a negative. So that means if I'm looking at the Pka values from lowest to highest for this structure, the lowest Pka looks like it should be hydrogen C, because that one actually, if it's donated, the negative charge mostly resides on the oxygen. The atom carrying the negative charge, oxygen, is better than carbon, and it also stabilized by resonance. So both those factors suggesting that the negative there should be more stable than any of the other negatives it results, and thus hydrogen C more readily given away or more acidic than any of the other hydrogens shown. Then I can say hydrogen D would have the next lowest, and they might be quite close because they're both stabilized by an oxygen atom primarily. Looking at the negative result here versus over here, they're both on a carbon. Neither one can be stabilized really by resonance. The fluorines are pulling electrons away, creating a little bit of a partial positive here, which is going to pull these away. It's going to create a little bit of a partial positive there, and that's going to kind of pull those away. So this hydrogen might be stabilized by induction. It's close enough to the fluorine. And fluorine is the most electronegative atom, so its ability to create induction is more significant than any other element. So having a fluorine there pulling these electrons away, even though it's a couple bonds away from the lone pair, it really does help to stabilize that negative. So I might put HB next and then HA. In a question like this, the order is not going to be that important. The explanation is much more important. It's much more important that you understand the concepts and how they apply to specific examples than that you're able to rank them for sure, because there are exceptions. Here over in this structure, or if you want to do the same analysis, I'm looking at the hydrogen or proton being lost and the electron staying behind to create a negative charge here. So there's already a couple lone pairs here. If this hydrogen does the same thing, I create a negative here because I'd have two lone pairs. If these electrons stay behind, I'd have another lone pair there. That would also be negative. So again, the quantity of charge in each case is the same. So I want to look at the atom carrying the charge. Can oxygen stabilize a negative better or worse than nitrogen? Well, oxygen's got one extra proton. It's a little bit more electronegative. So it should be able to hold any lone pairs it has a little bit closer to its nucleus and stabilize them better than nitrogen. So the lowest pKa for this molecule would be HA. For B and C, when either of those are donated, the negative resides on a nitrogen. So the atom carrying the charge is the same in each case. Then I got to look for resonance. Can either of these lone pairs be stabilized by resonance? Well, this one can't, because none of the 5 patterns, I can't use any of the 5 patterns to really move it around, and it's in an sp2 orbital anyway, because it's on an sp2 hybridized atom that already has its pi electrons involved in the double bond, and so it has to be in a p orbital to be stabilized by resonance. This lone pair down here, though, can be stabilized by resonance. So once this hydrogen's lost and the electrons stay behind on the nitrogen, I've got 2 lone pairs. One of those can exist in a p orbital and be stabilized by overlapping with the p orbitals in the ring. Or in other words, I can use my recognition that this lone pair is allylic to one of the double bonds in the ring. It can shift in here and move the negative to a carbon. Or this could shift around and move this negative to that carbon. Or this could shift in there and move the negative to that carbon. So actually the negative is going to be spread out over 4 total atoms once the resonance happens there. And so that should really stabilize that negative a lot more than just putting it in one single sp2 orbital on one atom and concentrating all that extra negative around one atom. So I can say HB should have a lower pKa than HC. Any questions about those? Alright, so as we were saying earlier, sometimes the acid won't already be neutral. Sometimes it might already have a formal positive charge. And that's why we're adding the extra letter in here, the C. So that counts for the quantity of charge. If it already has a positive charge, we won't be able to use aereo, but if we add the extra C in there and we can remember that, well, clearly if I have something like this versus something like this that already has a positive charge, I can easily tell that one is going to be much more likely to give up an H plus and become neutral than the other would be to give up an H plus and become negative. Right? So if they have different quantities of charge, generally I can say whichever one has more charge to begin with is going to be more likely to give up a proton to alleviate that charge than the other molecule would be to give up a proton and create an unnecessary charge. Right? So we know formal charges are unstable. We want to avoid them, and we can use that to help us rank things as well. So if we're ranking these 5 using the acronym, in this particular case, since they all have the same quantity of charge, this is not going to distinguish between them. It's not the same element carrying the charge in each case. So I then would look at the atom and ask myself, is oxygen better at stabilizing a positive, or is nitrogen? Well, in the last examples, we were talking about a neutral oxygen losing a proton and forming a negative versus a neutral nitrogen losing a proton and forming a negative. And we said oxygen stabilizes a negative better than nitrogen. That doesn't mean oxygen can stabilize any charge better than nitrogen. When we're specifically looking at a negative, the oxygen's extra proton helps to pull the negatives in and stabilize them by forming extra attractions. So oxygen is better with a negative. But if I form a positive, I kind of have the opposite situation going on. And this also relates to today's quiz question, because with the extra proton, it's already more electronegative than nitrogen. If I'm looking at them in their neutral forms, oxygen is more electronegative when neutral than nitrogen is when neutral. And that means it pulls electrons away from atoms it's sharing electrons with better than nitrogen does. So if oxygen's already more electronegative, it's already pulling the electrons away, that does make it susceptible to losing the proton and keeping the electrons behind. More so than is the case for nitrogen. So we already know that oxygen's a little bit better as an acid than nitrogen is because of the extra proton attracts those electrons. And so we'd have the same thing here. If I'm comparing oxygen versus nitrogen, the oxygen is, now that it's positive, it's even more electronegative than when neutral. But still, the difference between them is an extra proton in the oxygen versus nitrogen, right? 8 protons versus 7 protons in the nucleus. So the extra proton is going to act to pull electrons away from a hydrogen even more than nitrogen would. And I would expect these electrons to come back over here and stabilize the charge on the oxygen and be more attracted and pulled more often to the oxygen, donating a proton more often than the nitrogen would do that. So if we want to label these so we can rank them, we can say that if we're going from lowest pKa to highest pKa, the ones with the oxygens will be on the lower end, and the ones with the nitrogens will be on the higher end. So we still have to distinguish between them using the other letters of the acronym. So I know A, B, and D, I'm just going to put them here, will be on the lower end, and then C and E will be on the higher pKa end, right? These are weaker acids because they're less likely to have to give away an hydrogen if the positive isn't as unstable or if there aren't as many protons pulling electrons away from that hydrogen. And also, I just want to mention, in the last examples, we were analyzing the stability of the conjugates, and we were saying if the conjugate is stable, then the original substance is stronger or more reactive because it'll be more likely to produce the conjugate. If my original molecules are all charged, I don't need to look at their conjugates because I can look at how this acronym affects the stability of the charge, and I can say if it's already stable, it's not as likely to give away a proton, so it's a weaker acid. If it's unstable, it's going to be a stronger acid because it's going to need to give away that proton to stabilize and alleviate that charge, and that's going to give it a lower pKa. So that's why we're distinguishing these two groups. All right, so we're looking at A, B, and D. And so what are the differences? Well, each one, it's an oxygen carrying the positive charge. So then I got to look for resonance. Is there resonance to stabilize the positive charge in any one of these? Well, let's take a look at this first one, A. Yeah, there is. I have a pi electron pair shared between elements of different electronegativity, so I can shift the pi electrons, I can move them to the oxygen. And that would create an alternative resonance structure that would put the positive on the carbon instead of on the oxygen. So so this does break the octet for the carbon, but that's not impossible. So it's a minor contributor, but still significant. So in reality, the positive isn't in a really unstable way concentrated on the oxygen. It's really spread out over both the oxygen and the carbon. And that really helps to stabilize the positive charge. So since this is more stable, it doesn't need to donate the proton as much to alleviate the positive charge. So it's not going to be as reactive or unstable. It's not going to have quite as low a pKa as B or D. So we'll put A here on the upper pKa side of this grouping. So now we want to compare B and D. So the difference here is D has this extra pi system out here. So what effect does that have? Well, can it affect the structure and resonance? Can I move electrons in here to help stabilize that positive? No, definitely not. This oxygen already has 8 electrons. It cannot hold 10 electrons, so there's no resonance to really stabilize that. Is there induction? If there's any induction to stabilize the positive, that would help make it a weaker acid. It wouldn't need to donate its proton as much. Not really seeing that as an issue here because there's no elements with lots of electronegativity around. So then I want to look at the orbital that's involved. Well, the orbital is more for stabilizing a negative charge than for a positive charge. But let's just talk about it real quick. So if this oxygen is sp2 hybridized, it has a steric number of 3, so its lone pair is an sp2 orbital, versus this oxygen over here, it's got a steric number of 4, so its lone pair is going to be in an sp3 orbital. Oh wait, I'm not looking at that one. I'm sorry. We already distinguished A from those through resonance. Sorry. We're looking at B versus D. And we would put the lone pair in an S. They're both sp3 hybridized because they both have the same steric number. So this makes it really hard to distinguish between these two. So what this comes down to is the last letter of the acronym when distinguishing between B and D in this situation, and that's S. So I put the S in front of the acronym, even though the letters that come first are top priority when analyzing, and then the ones at the end are lower priority. The reason for that is because the S, which stands for solvation, can make a huge difference in the pKa, or it can make a very small difference in the pKa. So I put it here so that it creates a more cool sounding name, scario, than carios, if I had put it at the end. But I also put it here because there are situations where it really is the most important factor. Sometimes it's not really relevant. But in this case it is a little relevant. And that the way solvation works is it's when the solvent helps to stabilize a charge. Right? So we've been saying if this charge is really unstable, then it's going to make a stronger acid because it's going to need to pull these electrons in to balance out that charge. How does the solvent stabilize a charge? So solvation is where the solvent stabilizes the charge by forming intermolecular forces. So whatever the solvent is, if it doesn't say, it's assumed to be water. So to stabilize this positive, there'd be some water molecules that would come in and bring in some partial negative, form some attractions there. The more space there is to fit more water molecules around there and bring in a greater quantity of partial negative, the more that positive can be stabilized. And this is a huge factor. If I didn't have any, and that's why I'm putting this first in the acronym, if I didn't have any solvent at all, and I couldn't form any of these intermolecular attractions, this would be really, really unstable. Its pKa would be much more negative and lower by orders of magnitude than you would otherwise expect if there's solvent to come in. So the main difference between B and D here is I've got a couple extra carbon groups. I've got, actually let me do something really quick because this is getting really cluttered. I want to discard all this ink and go back in. Alright, so we can see this better now. So I've got a couple carbon groups taking up some space. That's going to kind of block out the ability of solvent to come in and bring in much partial negative to attract there. But here I've got even bigger groups. So this is a 2 carbon group versus only a 1 carbon group, and that's going to be blocking out the solvent a little bit more. So the solvent's ability to bring in a partial negative over here is going to be diminished when it's getting blocked out by this larger group trying to make it in there and form that attraction. So this one I would expect to be a little bit better stabilized by the solvation than the one that's more crowded around with other atoms already present that the solvent can't really get through to form nice intermolecular attractions between the partial negative and the full positive, the ion dipole attractions there. So if we're going from lower pKa to higher pKa, we could probably say that D has the lowest. It's the most unstable positive because I can't form much attraction with the solvent. It's got no resonance to stabilize it. It's got no induction to stabilize it. The atom carrying the positive is not as stable as it would be if it had fewer protons. And so D is the most reactive or strongest acid with the lowest pKa. Then I could say B, and then I could say A, because at least A is stabilized through resonance. As we said, the electrons can move out there and spread the positive over 2 atoms instead of 1. So then to compare C and E, I'm looking at the difference. The only difference I'm seeing is the presence of these fluorines. So the fluorines are electronegative. They're the most electronegative atom. They always pull electrons away from other atoms. That's going to create a partial positive. So in this case, the fluorines, through induction, attracting electrons away, creating a partial positive, that destabilizes this molecule. So if there were a negative here, it would stabilize it by forming an extra negative partial positive attraction. But if I already have a positive and I create a more positive on the very next atom, that only creates repulsion. That only causes a little bit more electrons to be pulled away from the nitrogen than would normally be pulled away, and that exacerbates the amount of positive here and destabilizes it even more. So this nitrogen is more desperate to give away its proton to balance its charge because it has more positive charge due to the electrons being pulled away from it by the fluorine. So that one is going to also have a slightly lower pKa and be more acidic than C. Any questions about that ranking? I know there's a lot there, so that's why you want to do a lot of the practice problems so that you can get feedback on those, find where you're making mistakes, and avoid those mistakes on upcoming exams. So as we were saying, pKa is definitely the best way to determine which side an equilibrium will favor because those are quantitative values, and we know the equilibrium will always shift toward the side with the higher pKa. What that means is if I have a reaction where I've got a couple reactants and a couple products, if I know one side has a higher pKa than the other, that tells me when it reaches equilibrium, the side with the higher pKa, most of the molecules will be in that form and very few will be in the other form. And that's helpful, right? If I'm running a reaction, I want to know, is this reaction actually going to go in the forward direction or are almost all the reactants going to stay in this form? There's no point in doing the reaction if all the reactions are going to stay in their original form because the equilibrium favors that side. And so that's a really important question for me to be able to answer. If I have the pKa's, I know that the side with the higher pKa is going to be the side that I have more of when it reaches equilibrium. If I don't know the pKa values, so like on an exam if they're not given to you, then you would want to use the acronym to help determine which side is more stable. So in that case, like in this example here, all you really need to do is focus on the areas where there's a charge and find a way, using one of the letters or more in this acronym, to determine how the charge could be more stable on one side of the equilibrium versus other. And whichever side it's more stable on, that's going to be the side the equilibrium shifts toward. You're going to get more of those substances than you would if they were less stable. So, unless the question says something about the solvent, usually I look at this actually last, so it really could be at the end. But if one of these molecules was in a different solvent for the other, and I was ranking their pKa's, then this would be the major factor. That's why I put it at the beginning. In this case, it's not going to really distinguish between these two structures, so I look at the next letter, which is the quantity of charge. Well, both have the same quantity of charge, so that's not going to help me distinguish between them. What about the atom carrying the charge? Well, they're both nitrogen, so that's not going to help me distinguish between them. I go to the next letter. Hey, wait a second. You got to remember, the atom that's shown carrying the charge may not be the only atom carrying the charge because of resonance. So if you forget to look for that, when you do get to the next letter in the acronym, which stands for resonance, look for it then. Right? So we want to look for resonance here. We can see that nitrogen can shift its electrons in and push them up to the sulfur. Same thing over here. So they both have resonance. And if I look at the other resonance contributor in each one of these, it's going to create a negative on a sulfur in this case versus creating a negative on an oxygen in this case. So now I can actually see a difference. So even though the atom carrying the charge initially wasn't different between the two structures, this negative is actually spread out evenly over the nitrogen and the sulfur. This negative over here is spread out between the oxygen and the nitrogen. So then I can ask myself, which atom stabilizes the negative charge better, sulfur or oxygen? Because that's really the only difference between these two structures. And this is where students sometimes make a mistake. Oxygen is more electronegative. If I looked at the electronegativity values, sulfur is about 2.6, oxygen is about 3.5. Oxygen is much more electronegative, so it attracts shared electrons toward it better than sulfur does. But when we're looking at the atom stabilizing the charge, remember the two factors we talked about in the beginning? The first one was size. The second one was electronegativity. But since electronegativity is something we talked about a lot in Gen Chem, I think students kind of gravitate toward that factor more often. So you got to check for size first. If there's a significant difference in size, that's probably going to be overriding any difference in electronegativity. So when I look at sulfur, what do I see for the sulfur atom? It's got 16 protons. So 16 protons with one extra electron making it negative would give it 17 electrons, versus the oxygen with 8 protons and one extra electron. Well, if I look at the charge ratio in both those cases, I can see a significant difference there. If I take 17 divided by 16, I get 1.06. If I take 9 divided by 8, I get 1.13. So this one only has about 6% extra negative compared to the amount of positive. This one has about 13% extra negative compared to the amount of positive. So that's about, in terms of the extra negative, it's almost double what the other one has. So with a charge ratio that's significantly closer to 1 or closer to being balanced here, this actually stabilizes the negative better than the oxygen. So this equilibrium arrow would be more looking like this, where once it reaches equilibrium, I should have more reactants than products. And if I could predict that before doing the reaction, I might save myself a lot of time and effort in the lab. All right, so another important skill is to select a reagent to cause a reaction. And this is where you'd be using the Pka values. So if you have the textbook out, you want to be referring to table 3.1 in the textbook. So we'll talk about these in reference to that table. So all this is basically saying is, if I've got a base, something with a negative or with a lone pair that's able to pick up a proton, and I want to put a proton on there, if I don't use an acid that's strong enough, I won't be able to. So how do I find an acid that's strong enough to put a proton on there? Well, if an acid did donate a proton to this lone pair, it would create this structure. And the pKa of that, given on table 3.1, is 25. So if I want to make sure that this actually happens, and I use an acid that's strong enough to put a proton on here and actually produce this product, I got to select something on the table that has a pKa lower than 25. If I select something with a pKa higher than 25, well, the equilibrium always will favor the side with the higher pKa. If I select something with a pKa of 24, well, it'll favor the side with the higher pKa. 25 is higher than 24, but it'll only be by a factor of 10. So if I want the equilibrium to favor one side as much as possible, I would use the lowest pKa possible. But basically, by checking the pKa of this molecule, I know that any structure with a pKa lower than that should be acidic enough to protonate it. So if I look on that table, any of the alcohols listed there, or the water, or the carboxylic acid, any of those should work. So if I want to use water, water should be fine. This lone pair would pick up a proton from water, and water's pKa is about 15.7. So I know that water will donate that proton and produce OH minus. And that equilibrium will greatly favor the side I want it to, because the pKa is low enough by enough factors that I should have 10 to the ninth more reactants here than products, if I think about this as the reactant side. Over here, this structure here has a lone pair. It could pick up a proton. If it picked up a proton, it would produce acetone, which has a pKa of about 19. So if I want an acid strong enough to do this, it has to have a pKa of lower than 19. If I want to protonate this one, it would form something that's positive. Right? The oxygen would have to use a lone pair to pick up a proton and form a positive charge. And so this thing has a pKa on the table of -7. So now I'm getting into the territory where if I want to put a proton on this oxygen, which starts off a certain reaction mechanism, and that's one of the reactions we'll look at later in the semester, and even more so next semester, if I want to force one of these lone pairs to pick up a proton, I need a really strong acid, because the acid I'm forming has a very low pKa. So I'd have to use HCl. Well, actually, HCl wouldn't even be strong enough, because its pKa is only 7. I'd have to use sulfuric acid from the list of table 3.1. There are other acids I could use, but just from that table, it's the only one that has a lower pKa value than the pKa value on that side. And since the difference is only 2 pKa units, it would favor the side I want, but only by a factor of 100 to 1, which isn't bad. So I mean, I can get that to happen using the pKa values. So that's how you use pKa values to force a reaction in the direction you want. Likewise, if I want to deprotonate a structure, I need to select a base that is strong enough to deprotonate my proton. Right? So in this case, what can I use to pick off this H from this H+? Well, if I look at this molecule, its pKa value is about 2, -2 I mean. So if this side is a -2, I want to shift it to the other side. I need to pick a base that when it picks up this proton, its conjugate acid that it produces has a pKa higher than this, right? Because we already said the equilibrium will always shift toward the side with the higher pKa. So I can look at the bottom of the table there, any one of those higher pKa compounds, I'm not going to use the acid, I'm going to use its conjugate base. So I'm just going to select one. I'm going to look at using the ethoxide. And if you look on that, now it's roughly in the middle of the table. It has a negative charge on the oxygen. When that picks up this proton, it produces ethanol. And ethanol's pKa, listed on the table, is 16. So that's definitely higher than the pKa on the other side, and that will ensure that my reaction goes to that side and that this H3O plus will be deprotonated to produce water. Right, so I can control which side the equilibrium favors by selecting the right compound from the table. We'll just do one more of these four. Let's take a look at this one here. This structure is listed on table 3.1. It has a pKa of about 10. Really it's listed as 9.9, but I'll just put 10. pKa of 10, so that's kind of in the middle of the table. If I want to deprotonate that and force it to lose its proton and produce a negative on the oxygen, I need something that I need a base so that when that base picks up that proton, it produces something with a higher pKa. Right? The equilibrium is always going to shift to the side with the higher pKa. So maybe I go with NH3. NH3 has a pKa of 38. That's much higher than 10. Right, so if I want that to form, I've got to start off by adding NH2 minus. Right, I'm not adding an acid to deprotonate an acid. I'm adding the conjugate base of the acid that I want to form. And I'm selecting an acid to form that has a very high pKa value to help shift that equilibrium toward the side I want it to shift toward as much as possible. So basically the pKa table tells me that this base is strong enough to deprotonate this proton. And by a lot, because of the difference in the pKa values there being so significant. Any questions about that? Alright, so a lot of times our instincts when we're doing reactions, especially acid-base reactions, is to do the reaction in water. And that will often work. This last reaction, though, let's just talk about the one we just talked about because it's a great example to illustrate the leveling effect in water. So I was saying I want to take this compound and deprotonate it. Why do I want to do that? Well, maybe I want to get that proton off of there so that I can create this negative charge on an oxygen. Maybe I want that negative charge, now that it's unstable, to start sharing electrons with the carbon and form a new bond here to create some new molecule that didn't already exist. Right? So that's one of the things we're going to talk about later in the semester a lot, how to use acid-base reactions and other reactions to manipulate the structure of this compound and make atoms bond the way we want them to bond so we can make interesting structures with valuable properties. So maybe I need to select the base to remove this proton and make this negative charge. And so on the last slide we said because this molecule has a pKa of about 10, we were going to use NH2 minus, and that would produce NH3. And since the NH3 has a pKa of about 38, that was a good choice because that negative can pick off that proton and the equilibrium should really greatly favor the product side because there's a much higher pKa over there than on the other side. I also have to concern myself with the solvent though. These pKa values are from reactions in water. So normally I'm thinking about water as my solvent. I can't lose track of the fact that the solvent is going to be surrounding all of these structures. But water isn't just a solvent. It also has the ability to act as an acid or base, as we said last time, and its pKa is about 16. So if water's pKa is about 16 and it's the solvent and it's everywhere, well, water also has the ability to react with this base that I'm adding. So I'm intending for this nitrogen's lone pair to pick off this proton and do this reaction and make this negative here so I can do something with it. But if water's my solvent, well then this nitrogen, instead of picking off the proton I want, since it's constantly surrounded by water, it's much more likely to collide here and pick off this proton. And when the nitrogen picks up a proton from the water, it will also produce NH3, which has a pKa of 38. And when this proton's lost, it'll produce OH minus. So I've got two different equilibrium to worry about at once. This NH2 minus could pick off either one of these protons. It could pick off this one and go over here. It could pick off the water's proton and produce these products over here. And since both of these equilibrium would be favored in the forward direction, since they both produce a pKa that was higher than the initial pKa, whether it's reacting with this molecule to make the product shown over here, or whether it's reacting with water to make the product shown over here, the product's pKa is higher than the reactant's pKa. in both reactions. And that happens a lot. So what that ultimately means is, if I add a base in water that's stronger than OH minus, it will just immediately react with water to produce OH minus. So I can't really get anything stronger than OH minus unless I use a different solvent. Likewise, if I try to react an acid, let's say I want to use HCl, since it's such a strong acid, and I want it to react with, let's say I want it to react with, let's say I want to use it to protonate this carboxylic acid, the conjugate base of this carboxylic acid right here. So I want to force this oxygen to pick up this proton. Well, if I use water as my solvent, just like water can act as an acid and donate a proton, it can also act as a base and pick up a proton. So that proton is intended to protonate this oxygen, but it might instead protonate the water. If it protonates the water, I get H3O+. So is that going to happen? The way for me to know if that's going to happen is to check the pKa units, the pKa value. So HCl is a pKa of about -7. H3O+ on the other side of that equilibrium has a pKa of about -2. So -2 is larger than -7, so this equilibrium would favor H3O+. So if I have water around, I have to remember it's going to be colliding way more often than anything else because it's my solvent, it's everywhere. I can't use an acid any stronger than H3O+ in water, or the acid will just react with water to produce H3O+. And I can't use a base in water that's any stronger than OH-, because if I do, it'll just react with water and pick off a proton and produce OH-. So if I'm expecting to pick off this proton with NH2-, it's not going to happen. It might get picked off by the OH-, but the NH2- is not going to be around in water. Just like HCl is not going to stick around in water. It's always going to produce H3O+, because H3O+ is more stable and has a higher pKa value than the HCl itself. Right, so this what we're illustrating here. Right, if I want to use this compound to act as a base, I can't do it in water because it'll just react with the water, and then the base I'll really have around is OH-. I can't use sulfuric acid to react as an acid with some other compound if water is the solvent, because if water is a solvent, it'll just react with water. The water will pick off the proton because water's the conjugate acids of water, its pKa is much greater than sulfuric acid. So if I want to use sulfuric acid to put a proton on something, I need a solvent that isn't also going to instead pick that proton up. That's the key thing here. Here's another example. Maybe I want to use this, as we were saying, here's a rare example where the negative is less stable on a nitrogen than on a carbon, and that's because the more compact sp orbital stabilizes the lone pair better than the more elongated sp3 orbital. So in this reaction, I expect this nitrogen's lone pair to pick off this proton, these electrons stay behind on the carbon to create that negative. How do I know that? I know that because the pKa of this conjugate acid of that substance is going to be about 38 roughly, and the pKa of this compound, very similar to acetylene on table 3.1, it's going to be about 25. So I know the equilibrium is going to shift toward the side I want it to shift because that's the side with the higher pKa. I can't do this in water though, because as we just said, the water would also protonate this nitrogen, and since it's all around, it's just much more likely to collide there, and that would produce OH- and the conjugate acid of that nitride. And again, this would have a pK of about 38, the water has a pK of about 15, so it's still going to shift toward the side with the higher pKa. So I can't use water. I need this nitrogen's lone pair to pick off this proton, not the proton from water. So I can't put water in. I'd have to put something in that's called aprotic. Something that's not protic. Something that has such a high pKa value that it's so stable it won't donate any protons. That way, the lone pair I want to pick off this proton will pick off the right one. So I got to look at these pKa values. Here, this is an alcohol. It's very similar to a couple of the structures on table 3.1 that had pKa values about 16, 17, 18. So the pKa of this is about 17. Is that going to work? No, that's almost the same as water. It's going to donate a proton to that nitrogen just like water would. And when it does, it's going to create a base similar to OH minus. OH minus is not strong enough to pick off this proton. Right? So, or in other words, if all of these molecules pick off a proton from water or from this molecule to produce OH minus, or in this case, this oxygen with a negative. Oxygen with a negative is not unstable enough to pick off this proton and create carbon with a negative. Oxygen is more stable than carbon with a negative, even when I'm looking at sp3 difference in the orbital. And I know that because if I try to use this to pick off this proton, the products that would be created would have a pKa of about 17. Well, if this structure picks up a proton and it gives a pKa of 25, that's a larger value. So that equilibrium would actually just go back. Right? The equilibrium always favors the side with a higher pKa. So I can't use a solvent who's got a lower pKa than the pKa of the substance I want reacting. So I've got two other options here. I'll call this A versus B. Both of these are aprotic. They're both good options. They both have hydrogens only attached to carbons that are sp3, so they're not acidic. Their pKa value is going to be closer to 50, so they're very stable. They're very stable. I don't have to worry about them reacting and donating any protons. So how do I know which is a better choice? Well, we generally avoid completely non-polar solvents. There aren't many reactions where I'm going to get a good yield of the product if my solvent is totally nonpolar, and the reason for that is because nonpolar solvents just don't dissolve polar substances or charged substances because they can't form very strong intermolecular attractions. So choice A here is better. It's unreactive. It's got such a high pKa, it's not going to react, but it's still polar due to the electronegativity difference here. It still has a negative end and a positive end. So it can still form a dipole and maybe surround these structures and form some ion dipole attractions and surround the structure and bring everything together and help facilitate the collisions between the molecules that I actually want to react. So designing a reaction is not easy. There's a lot that goes into it, especially if it's an acid-base reaction. You really got to look at those pKa values and make sure that the solvent you're selecting is effective as well as the acid or base that you're selecting to perform the reaction. So we talked about solvation a little bit. We'll just look at another quick example. So, I said put the S for solvation at the beginning of the acronym, because sometimes it really makes a huge difference, sometimes not so much. So let's first look at a situation where the difference the solvation makes is relatively minimal. So if I'm comparing the pKa's of these acids or their ability to donate a proton, if this one donates a proton and the electrons stay behind, it's going to create a negative charge on an oxygen. If this one donates a proton and the electrons stay behind, it's going to create a negative charge also on an oxygen. So the quantity of charge is the same in both conjugates that I'm trying to decide which is more stable. The atom carrying the charge is an oxygen in both cases. There's no resonance in either case. There's no real induction to help spread out the negative over multiple atoms. In both cases, it's an sp3 orbital that holds the negative charge. They're both sp3 hybridized with steric number of 4. So none of these factors explain the difference. Solvation is the only one. Right? So what we said, solvation is where the solvent molecules come in and surround the charge to help stabilize it. Right? So all these other factors, the cario in scario, all these other letters in the acronym are ways in which the molecule can stabilize itself through induction or resonance or whatever. Solvation is the only one where the molecule gets stabilized by other molecules coming in. And so the pKa difference here is explained by solvation. So there's a nice picture here on this slide that shows that. Right, so when I put all these carbon groups over here, they're all taking up space. The electron cloud of this is quite large. So it's really all over here, kind of blocking the solvent from coming in, except for in a couple spaces. So my solvent's probably going to be water. Whatever the solvent is, it's going to have a dipole, and it's going to bring in some partial positives around to attract to that full negative charge on that oxygen. But if most of the space around that oxygen is blocked by this large crowded group of carbons and hydrogens and their electron cloud, I can't really bring much solvent in there. It's only going to be stabilized to a small extent. If I have a smaller electron cloud, I can fit more solvent molecules with partial charges around the negative charged oxygen to form more attraction. So even though these two are in the same solvent, the sterics or crowding associated with the more bulky molecule prevents the solvent from as effectively attracting to that negative. And so that means, if I look at the Pka values, the negative that would form here would not be as effectively stabilized. So it would be often picking that proton back up, which means it's not a strong acid. It's not going to lose the proton and keep it lost. It's going to pull it back. And so its Pka is just slightly higher than the other molecule's Pka. This molecule will exist more as its conjugate base because it's more effectively stabilized by solvation. And so if it doesn't react back as often, it's a slightly stronger acid with a slightly lower Pka than the other structure. If I'm looking at a situation where I'm comparing two different solvents, and this is why I put solvation in the front of the acronym, then I see a huge difference in the Pka values. So if I'm looking at acetic acid, for example, we normally think of acetic acid as having a Pka of about 5. And that's because when it loses its proton, the electrons stay behind. It's nice and self-stabilizing through induction and resonance. Electrons are actually spread out over both oxygens. So I've got that negative spread out over both atoms. That's only true in water, where its Pka is so low because it will so readily give up a proton and stabilize the negative charge. The resonance really helps stabilize it, but the fact that water is the solvent and water molecules can bring in a large partial positive to also attract to the negative that's spread out over those two oxygens, that really helps to stabilize it and makes it a much better acid. If I do the same thing in a different solvent that's not nearly as effective at bringing in a partial positive, like water can bring in a hydrogen bond here, form a nice strong ion dipole attraction. If I have a different structure like CH3CN, which has this Lewis structure, here the partial positive is surrounded and kind of blocked out by this group. So it's harder for this molecule to get in here and bring in its positive to help stabilize the negative. So if the solvent is less polar or less able to form strong intermolecular forces with the charged conjugate, then the original molecule is not going to be nearly as likely to form that charged conjugate. And that's reflected in its much higher Pka value, showing that this molecule is much less acidic, much less likely to donate a proton and form a negative in a solvent that can't bring in much positive to stabilize that negative very effectively. Alright, so that brings us to the last, there's a couple other things here, almost out of time. Yeah, let's talk about this quiz question though. So I had a chance to dialogue with a couple groups already about this. If you get your quiz answers at least started early enough for me to check out your Google Docs, I can give you some feedback and help you in the right direction here. So we want to use the acronym to rank these. And what we're seeing initially is, it doesn't say anything about the solvent, so we can assume they're all in the same solvent. So that may or may not play a role in the ranking. So we'll leave that out for now. So definitely the quantity of charge is going to play a role though. So if we're going from strongest base to weakest base, the ones that have full negative charges are very likely to pick up a proton, so those should definitely be the strongest. So we can put B, D, and E over here. The ones that are already neutral, they don't need to pick up a proton. That's only going to make them positive. It's going to make them less stable. So they're not going to be likely to act as a base. And so we can put A and C over here. We also have to recognize the relationship between how strong the base is and what the pKa value will be for the conjugate acid. All right, so let's just take a look at one of these. If this one, which looks really unstable because the negative formal charge is on the carbon, if it were to pick up a proton, it would be extremely stable. It would really stabilize that negative. And so if it's a stronger base, its pKa has a higher pKa value, the pKa of its conjugate. So the stronger the base, the higher the pKa of the conjugate. And so on this side we would have lower conjugate pKa values. Alright, so we decided that B, D, and E are all very unstable because they have a negative charge. So we have to decide between them which can stabilize the negative charge most effectively. And since it's the same quantity of charge on each, we then look at the atom stabilizing the charge. So here I've got a carbon stabilizing the charge, here I've got a carbon, here I've got a carbon. So that's the same. So then I go to the next. Is there resonance to stabilize the negative charge in any of these? And the answer is no. Each one of these lone pairs exists in a hybridized orbital. This one's in an sp2. These are in sp3s. There's no nearby p orbitals with which they could overlap if they were to go into a p orbital, and so there's no resonance. None of the 5 patterns work for any one of these structures, so resonance is also not a factor in ranking these 3 against one another. So then we look for induction, and that's what the fluorine is doing. The fluorine being bonded right here is pulling electrons away. It's attracting the shared electrons away, and so there's really less electron density right around this carbon than there would be otherwise if there were no fluorine there. And so by pulling electrons away, this carbon doesn't hold a full negative. It only holds a partial negative because these electrons really get pulled away pretty effectively, versus over here, there's really nothing to spread out that negative charge. So we can say B is the strongest. D and E both have that induction to pull the electrons out so they're not so concentrated all in that area, creating so much instability. This one really needs to pick up a proton because it's really unstable as it is. So then the difference between D and E is a difference in the orbital. D has a slightly less compact, more elongated orbital. The sp2 orbital is a little bit more compact, so here the electrons will be held more tightly to the nucleus and effectively stabilized by that. So that means B is the most unstable, strongest base with the highest pKa for its conjugate, and next would be D, and then E. Right, so we've ranked those 3. Now we want to look at A and C. We said they're both neutral, and so they're not nearly as likely to pick up a proton and become positive as the other ones were likely to pick up a proton and become neutral. But we do want to look at their possibilities of picking up a proton. So if this one picks up a proton, it would use the lone pair from an oxygen. It would create a structure that looks like this. If this one were to pick up a proton, it would create a new bond there. So now that I recognize both of their conjugates would be positively charged, I can look at the quantity of charge as being equal on both of them. And so then the next thing I look at is the atom carrying the charge. So before I even get to the fact that there's resonance or whatever, if I have an oxygen carrying a positive versus a nitrogen, there's a difference in stability. Right? Oxygen has an extra proton compared to the nitrogen. So the proton in the oxygen is going to be pulling these electrons away from this other proton more strongly than the nitrogen is going to be pulling electrons away. So this one is less stable. It's not as likely for the oxygen to act as a base and pick up a proton if it's then just going to pull the electrons back from the proton because it's so electronegative, and positively charged makes it even more likely to be electronegative and pull electrons away. So we can say that the next strongest base would be C. It'd be more likely to pick up a proton since it doesn't form quite as unstable as a positive charge versus the oxygen. Even though there's resonance that can push some of these electrons out here and share the positive with the carbon, the majority of the positive is on the oxygen due to that being the major contributor, the one I've shown here. And so that is going to be pretty unstable if it picks up a proton. Not very likely to pick up a proton. It's going to have a very low pKa value if it does, because it's going to create a pretty strong conjugate acid, meaning that the original compound is quite a weak base. So I'll definitely give you individualized feedback on your work there, and the explanation is more important than the ranking. So look for any comments I make to help flesh out the details with your explanation. This slide is really not that important. Basically, the idea here is just keep in mind that if you have a charged species, you can't just buy that. You can't get it off the shelf. You can't have a bottle of chemicals where every chemical unit has an overall charge, because they would just all repel one another. So there's always a counterion. There's always something with enough opposite charge to at least counter that and make sure that the net overall charge in the reaction is 0 or in the bottle is 0. We often don't show these, though, because they're not involved in the reaction. They don't break or form covalent bonds. They don't really lose or gain electrons. They're just there to balance the charge. So it's really just a distraction often to write them. But you do need to recognize that they're there. Any charged species has to have a counterion of the opposite charge around within the system. And so then the last concept is the Lewis acid-base concept. This is going to be really pretty relevant to what we're working toward, a variety of chemical reactions. So any acid-base reaction, by the Bronsted-Lowry definition that we've been talking about, where a proton is donated to a base, can also be described by the Lewis definition. So a Lewis acid starts accepting and sharing a pair of electrons. Right? So that's exactly what we see here. My Bronsted acid is donating a proton. That's the Bronsted definition. It's also accepting and sharing a pair of electrons. So that's the Lewis definition. So they're just kind of looking at the same process from a different perspective. We're not looking at it from what's happening with the proton. In the Lewis definition, we're looking at it from what's happening with the lone pair of electrons. So the base is still the substance that shares its electrons. We can think of it as picking up a proton, or we can just think of it as sharing its electrons with something. The acid is the one that has an atom susceptible to sharing electrons with new electrons that come in. And so same definition, same species that we would have labeled a base under the Bronsted-Lowry definition, we also label it as a base under the Lewis definition. The Lewis definition, though, is more broad, and it covers reactions that the Bronsted-Lowry definition doesn't really think of as acid-base reactions. So here, this is not an acid-base reaction by the Bronsted definition because there's no proton being transferred. But it is an acid-base reaction by the Lewis definition, because the Lewis definition tells me that the base has a pair of electrons. It's going to start sharing with something, and the acid starts to accept and share those electrons into its outer energy level. So there are a lot of reactions that fit the Lewis acid-base reaction definition, and we're going to talk more about that as we continue forward. So that's basically all we have for today. Make sure you're prepared for the exam that covers the day 6 content. Believe that's going to be the exam that's happening next week for most of you. So practice up with the questions in the textbook, and then we will continue with chapter 4. That completes chapter 3. We're going to start up with chapter 4 on Thursday. So I know there's some confusion. Typically at this point, day 1 through 6 is usually the stuff I would cover on the first exam in a pre-COVID semester, when we would have only 4 exams throughout the semester instead of an exam every week. I think our current system is working well, but the reason that there's no day 7 is because that's normally when we would have our first exam. But we would set that whole entire day aside. We wouldn't cover lecture that day. We would just have our exam that day. But since we're having short exams on a weekly basis in lab, we can continue lecturing every Tuesday and Thursday at the normal time. So we will have a lecture on Thursday, and that will be the day 8 content, and that will be the beginning of chapter 4. So you want to try to look at some of that stuff and use it to help you answer the day 8 quiz questions, which are due on Thursday of this week by 1 p.m. Any questions about anything?
For SP, SP2, and SP3 orbitals, they all differ in just like the length, and I guess like P character to S character, not like they don't look like really different, I guess, in terms of composition.
Yeah, the roughly the shapes of those 3 orbitals, SP, SP2, and SP3, are basically the same shape. They each have that double lobe where one lobe is more electron density than the other. But they are, due to the extra P character, as you said, in some of them, the SP3 is more elongated due to the extra P character, and then as you get closer to the SP, where there's more of a balanced ratio between S and P, that causes the shape to be a little bit more compact. So it's not a major difference in shape because they're still mixing S and P, but as you said, the ratios do affect primarily the average distance the electrons are away from the nucleus. In a more elongated SP3, they're going to be farther out from the nucleus than in the more compact SP. And so that affects the stability of the electrons in that orbital, because the electrons are more stable the closer they can get to the nucleus.
So then do like the anti-bonding orbitals and the nodes, do they follow the same like pattern for all 3 then?
Yeah. As far as that goes, it's pretty much the same. The differences there are negligible.
Okay, thank you.
Yep. So there was a request. I know we're obviously past the end of lecture. There was a request to discuss some of the Lab 3 ideas to help you all get started with your Lab 3. So I just want to give a little brief lecture about that to give you some of the helpful information to get you started with Lab 3. So if you haven't yet seen, there's a video I made over the weekend showing the TLC demonstration. The TLC, or thin layer chromatography demo video, is up on YouTube. There's a link on Canvas. If you can't find that, let me know. And Cindy is asking a question right now that's related to that. So that video I made over the weekend is meant to help you answer the questions on the handout, right? So if you look at the lab handout for Lab 3, there's lots of pages. A good deal of that are just questions that you're meant to answer as a group. So you don't have to turn that in individually. If you create a group Google document for that, then you can all work on that together and turn in one for your group. If you can't agree on answers, just message me. I can help explain things and get you all on the same page. But most of the information in the demo video should help you answer most of those questions. And again, that you can do that as a group. That doesn't require you to actually do any experimentation, since I did that as a demo. Normally we would have the students do that, do an experiment related to TLC rather than just doing the demo, but it does use up a lot of solvent when you're doing it over and over again. So just to save on waste material, we're just using the demo video to help you answer those questions. So the experimental part for Lab 3 is where you are working with chromatography. It's not thin layer chromatography, it's a version of column chromatography. To separate impurities from mixtures. So if I have impurities that I want to remove, and that's a very common thing, because when you do a chemical reaction, it's very difficult to remove every impurity and isolate only one type of chemical unit from that complex mixture of reactants and products and side products and solvents and all these things. So removing impurities is a good deal of what organic chemists do, and that's why we need so many techniques to do that. So we've already talked about recrystallization as a way to do that. We've now also talked about fractional distillation in Lab 2 as a way to do that. And so here we're going to talk about chromatography. There are many different forms of chromatography, and that the form you use depends on the chemicals you're working with and what the impurities are and what you're trying to remove. So it's hard to know exactly what form to work with, but it is the most common way of removing impurities for organic chemists because there's so many different versions of it. So the specific situation you're going to have in Lab 3 in the experimental part is you're going to be given this low polarity compound that is neither an acid nor a base. So it does have some protons, but the pKa value of those protons is high enough that it's not going to be donating any protons unless you use a really strong base, which we're not going to do. And if it were to act as a base and pick up another proton, it would create an acid with such a low pKa, it would be very unstable, it would just give away the proton right back again. So this structure of this compound is called benzoin. You can check out its structure if you Google it. It's basically a compound that doesn't have much reactivity, but we want to remove some impurities from it. So your group will be given one of two one of two mixtures. You'll either have benzoin with an acid, a weak acid impurity, or you'll have benzoin with a weak base impurity. So a lot of times when you run a chemical reaction, you know what the impurities are likely to be. And there are ways to analyze the products of that reaction to see if those impurities are there. So you could easily run into a situation where you know that you have a weak acid that's an impurity and you want to remove, or a weak base that you want to remove. So what we're going to do is we're going to use these little plastic columns that are have an opening at the bottom. And we're going to pack this with a material that will pull out either a weak acid or a weak base from the benzoin, allowing the benzoin to drip through. So what do we want to use to do that? So a weak acid usually has carboxylic acid structure, and a weak base typically has a nitrogen with a lone pair. Could have multiple hydrogens, could have multiple carbon groups, right? So remember, R represents some group of carbons. So what do I need to remove this acid from my benzoin mixture and have the benzoin come through in its pure form? Well, the idea here is, first thing we're going to do is put a little piece of filter paper in here, specially designed piece of filter paper to fit into these little columns. It's going to be a little round thing. It's called a frit. Frit is just another word for a thick piece of filter paper. And that's just going to help so no solid comes through here, just liquid. And then we're going to pack on top of here a layer of ion exchange resin. And there are two forms of the resin. One meant to remove the acid, one meant to remove the base. So what's going to happen is this resin is going to be consisting of tiny little pieces of polymer, and they're going to be really tiny. It's like a powder. That powder, if you zoom in on it with a microscope, those tiny particles of solid making up that powder there's two options. You have a basic form or a protic form. So some of the powder we have has a base attached to it. So there's little basic sites attached to the particles of powder. The other particles of powder have acidic sites. So they have extra protons attached. The benzoin is not going to react with either of those because it doesn't really act as an acid or a base. So when you take your unknown, it's not an unknown, I keep saying that. When you take your benzoin and you dissolve it in ethanol with the impurities, because they're just in there, you can't see them or remove them effectively very easily. This is our method of removing them. If you take all of that and you put it onto the column, we want the impurities to get stuck to these little tiny particles. And we want the benzoin to go through. The benzoin's not going to react chemically. It's just going to travel right through with the ethanol, which is also not going to react chemically. So that mixture is just going to travel right through. So anything you collect should be a mixture of benzoin and ethanol. You can evaporate the ethanol and save the benzoin. But the impurities are going to react with these little particles in here. And they're going to produce charges, which is why it's called ion exchange resin. So what's going to happen is an acid-base reaction here is going to donate a proton from the acidic site to the basic site. And that's going to turn this molecule into an ion. It's going to give it a negative charge. Likewise over here, this nitrogen is going to pick off a proton from the little particles of solid that are inside that powder. And that's going to produce a charge as well. Oh, the hydrogen. Producing charges on the structures, and then when these little areas of groupings of atoms on the solid particles that are in there, when they react, they'll also produce charges, right? If this electron pair stays behind, it'll create a negative. And if this nitrogen picks up a proton, it'll create a positive. So the chemical reaction that occurs in here should, if things move through slowly enough and you give time for that reaction to occur, it should allow, if your impurity is an acid, you want to use the free base form. That will pick up a proton from the acid, produce two charged particles that now attract much more strongly. And that ionic bond attraction that they form should cause the impurity to stick to the column. The opposite charge attraction should cause it to stick to the column instead of running through. If your impurity is a base, you want to use the protic resin. The resin that has protons, so the base can pick up that proton, become positively charged. The electrons that were shared with that proton will stay behind and create a negative charge, and then these two will attract through an ionic bond attraction. And the basic impurity, which is now converted into its conjugate acid, because it's fully charged, should also stick to the resin and not pass through. And then when your liquid passes through, all you have to do is evaporate off the ethanol to recover what should ideally be pure benzoin, which you could confirm its purity with the melting point range. So if you have multiple people coming in on different days, each person could run this experiment in a slightly different way. So one person could use more ethanol, one person could use slightly more or less of the powder or resin that you put in there. One person could mix everything together and put it on there and then add extra ethanol and try to run through like extra liquid and collect more to see if you can recover more of the benzoin. But you might also get the impurities out, so you want to pay attention to the different variables that you could change from one student to the next to see how those variables affect the outcome of the experiment. And what that means is if you are going to do this individually, you don't want to use your entire sample so that the other students in your group, when they come in, can also try the experiment in a slightly different way, and you can make conclusions based on slightly different outcomes that happen when you change the variables slightly. So if anyone's still out there, I hope that was helpful. Does anyone have any questions about anything else?
If we still need to work on that too, or we have the materials for that, like
Yes. Yeah, I should have mentioned that. There's a couple groups now that are only down to 3 students, so some of you have not had a chance to finish Lab 2. I think that's only the case for one group at this point, but yeah, if you want to do more distillations or solubility profiles for any of the liquids in your Lab 2 unknown, you can definitely do that today. If you don't start on Lab 3 today, that's fine. Your group doesn't have to do 4 different versions of this experiment that are all a little bit different. You can do 2 or 3, that would also be fine. So, any other questions about anything? All right, everybody. Some of you I'll see in a couple hours. The rest of you, or really anybody, send me a message anytime you have any questions. Have a great night. Morty. Jump up here. Yes. I love you. You're such a good boy. I'm sorry I can't play with you while I'm lecturing. You're such a precious little boy. Jeez, buddy. Take it easy. What's up, man? Oh, gosh. Oh, my goodness.